Okay, this course is all about understanding images. There are relevant courses again on images that work on images, but it is good to know the crisp boundary between those. For example, one of these areas is known as image processing, and the other one is known as computer graphics. So what is mainly the difference between computer vision, image processing, and computer graphics? In image processing, what we really do is, think about an image processing system. Image processing system will input an image, it will take an image, and it will generate another image. So the input is image, output is image. Inside that, maybe some filtering will go on, some sharpening will go on. Aesthetically, the image may become more visual or more contentable and stuff like that. So image processing actually takes an image and returns an image at the end of the day. On the other hand, if we see computer graphics, it takes actually, if you think about computer graphics system, the system for computer graphics, it actually inputs a description or maybe certain cues or certain decisions or something like that, and the system outputs an image. So maybe, for example, a description, and based on that description, build an image that follow that description and stuff like that. So in computer vision, the idea is actually reversed, like in computer vision, like in computer graphics. For example, in computer vision, think about a computer vision system. The system will take an image as an input, and the output will be a description or the understanding of the content inside the image. So that roughly is reverse in order as compared to computer graphics. But if we talk about image processing and the methodology of image processing is actually used both in computer vision and computer graphics as a part as well. So and further, the advanced form of computer vision is, again, in terms of deep learning, is based on neural networks, specifically called convolutional neural networks. And we have a full-fledged course on convolutional neural networks as well. And even in this course, we have discussed a very powerful object detector based on the advanced computer vision techniques known as convolutional neural networks. So that's about the overall schema of what is computer vision, what is image processing, what is computer graphics, and particularly what is advanced computer vision. In this particular course, we will start from understanding the images. And in particular, we will start from image transformations. So if you want to, for example, rotate an image, if you want to scale an image, if you want to reflect an image, if you want to shear an image, and if you want to apply any of these kind of transformations in combination to come up with a new image. And in most of the cases, these transformations are required to build large panoramas and to actually register one part of the image with another one to build the traces and tracks. And for that, we need understanding of images. What are images? What are the data structures used to store images? And what are the color spaces that are available? What kind of transformations are there, known as geometric transformations? And given to images distorted by geometric transformations, how one can recover transformations. And this last part is heavily used in panoramic stitching, building large panoramas. So after this section, the viewer will be very much equipped with what are the images and how to play with those images, and in particular the geometric transformations. And by the way, we have written line-by-line code for each and every step. Whatever we explain, we have written code in Python, and not in OpenCV. We have written code completely in NumPy. We basically regenerated, for example, if you think about OpenCV, maybe you write one line and you do a lot of stuff. But what is the implementation inside the function? We build those implementations line by line in NumPy. And along with that, we wrote the OpenCV functions as well. So for example, first we display the information in front of you that this is the algorithm, that's the coding in NumPy. And then this is the OpenCV code for that. So that will help if one want to customize the code and one want to know what is happening behind the function and all that details. And this is true for all the sections. We carry this kind of particular kind of scheme in all the course. So we wrote most of the code in NumPy, and then we then we show the OpenCV function for that. And by the way, all the algorithms we are showing here, you will be seeing its implementation in NumPy in step-by-step live coding. Yeah, that's cool. After image transformations, we move towards image processing. In image processing, we use image filtering primarily for blurring an image, sharpening an image, and what are kind of convolutional filters. And we also talk about morphology to mostly denoise the final results. So the binary morphology, a lot of schemes that are there, they are discussed as well as coded. After that, we move towards edge detection. Edge detection is actually the boundary detection where the color changes significantly. It turns out that the most of the advanced shape detection algorithms, they rely on edge detection. And not only the classical computer vision techniques, but the very advanced convolutional neural networks. It is reported that the very early layers of very advanced convolutional neural networks, they are actually doing edge detection. So spending time on edge detection, which looks like the basis of a lot of object detectors and shape detectors, it is good to spend some time. And we cover a very famous algorithm in edge detection called Canny Edge Detector, and we code that algorithm in NumPy. How cool is that? After edge detection, we move towards the general shape detection. And the algorithms we cover there is RANSAC, Random Sampling Consensus, and Hopf transformation, very famous algorithms for detecting parametric shapes. And we also show that the RANSAC can be used not only to detect general shapes, but any kind of models, particularly for recovering an estimation of the transformations in the first section. After going through this shape detection, we move towards corner detection. It turns out if you want to build very large panoramas, if you have a lot of images together, or if you want to reconstruct 3D from a couple of images from the same 3D scene, it turns out we want to locate the points of one image and another image, and we want to join them, we want to match them if they are available. And the observation is that the corner points, the points where the two edges are meeting, these are the points that are easily locatable. So we spend a whole section on corner detection, and we covered a very famous algorithm known as Harris corner detector, and actually we wrote the code for that and show the results. It also turns out that these corner points, they are also known as interest points, have a lot of applications particularly in building large panoramas, in 3D reconstruction, then point matching, even in tracking. And the other thing about that is these interest points, they can be detected for variants for different scales as well as for different orientations. They can have different orientations, they can be detected at different scales. So we covered one algorithm known as scale invariant feature transform, and which is very state-of-the-art method for detecting the interest point as well as building the descriptors around it to match. And after the scale invariant feature transform, building panoramas, big panoramas, along with the very first section, the two sections, they are combined together and one can build panoramic application. Then we actually show the results of automatic panoramic stitching. After that, we move towards general object detection, and primarily we covered the classical techniques in generic general object detection, particularly known as template matching. Matching template for different scales and orientations, and we saw the limitations of classical techniques, and then we moved towards the YOLO, which is the advanced object detector, very much advanced object detector based on deep convolutional neural networks. Till now, we worked all on static images, but we never worked on videos. A video is simply a sequence of images, and it turns out if you play that sequence very rapidly, you can view that certain objects are moving in time. So then we moved towards motion, and we found optical flow, which is which pixel is going where in time. And that actually helps, this study actually helps in tracking objects in videos. And we spend a lot of time on building the object trackers. And we also relate these object trackers with corner detections as well, because on certain objects, if we can detect certain corners, corner points called interest points that can describe the object, we can just track those. And in that, we discussed one very powerful algorithm known as KLT, Kanade, Lucas, and Tomasi tracker. So after that, we move towards three-dimensional reconstruction of points. What camera does is it takes a 3D scene and projects it to two-dimensional images. The reverse process is known as 3D reconstruction. And for that, it turns out that we need the camera parameters as well as more than one images. And we rushed through this camera calibration and 3D reconstruction. One can have a full-fledged course on that, but we discussed very important and primitive points in that area. And finally, we built a very large project called Smart CCTVs. What happens in CCTVs, they are dumb. They see everything and record. They see everything and they just store without actually tagging what is happening and where it is happening at what time. What if you want to build a CCTV camera that just store things that are interesting? Not only interesting, it actually make it digitally searchable. So for example, if one wants to know who appears in this particular interesting stuff, then at that particular time. So for example, if a CCTV camera is looking for the last, is storing every frame for the last 72 hours, and in that time period, only a 3-minute clip was interesting, some change, some important change has happened there. Some person arrives or some object arrive or removed from a particular field of view. Then the CCTV camera should record, first of all, should record only that scene. And second, it should make certain alerts to owners or competent authorities. And not only that, if that is a person, if the entering or the exiting object is a person and is doing particular activity, one can just store that particular clip tagged with what activity it was performing, so that later on one can search digitally that I want to know all the video clips that belongs to theft activity or something like that. So we built that project completely based on the knowledge we just covered in the whole course. So the course is fun, complete of Python coding, NumPy coding, as well as OpenCV package. And particularly for YOLO, we discussed CVlib library based on TensorFlow as well. So have fun. I mean, that's a great course. From our side, we are really confident that's the best course in its own nature. Good luck.